Okay, it's time. I'm glad we didn't lose too many people. It's a great pleasure to be here, to be part of this course. I'm not sure I'm allowed to say this, but Pietro, Ashutosh, and I are writing a book on mixed integer nonlinear optimization. And you are not part of a GIAN course, you're actually guinea pigs on which we're trying out some of this material. So welcome to this little lab experiment. And before we start, whatever you do in this course, this is the most important slide of the whole course. So if you do not get this slide, you're in trouble. Please ask questions. So, there are no stupid questions. There's only people who can't explain what they're doing. And believe me, because I've seen it myself, if you have a question, then somebody sitting next to you has probably the same question. I've been in a talk with I was sitting next to a member of the National Academy of Sciences of the United States, Margaret Wright, and I turned to her and said, "Do you know what matroids are?" And she turned to me and said, "No." And I thought, okay, so we're both in the same boat here. So please ask questions. And then if you ask questions, at least I know you're interested and not solving Sudoku puzzles on your phone. Most importantly, I'm not a teacher. I work at Argonne National Laboratory, which is a Department of Energy lab. We do open science research there. We work on energy things related to energy. We work on new materials for energy, scheduling of renewable energy. We have a very large computer, but I'm not a teacher. So I learn from your questions, and we learn from your questions as to what do we need to put into the book. Okay, so I'm going to go quite slowly here initially and talk about the components of an optimization problem. And I should really apologize, because most of you, when you introduce yourself, we're basically saying, okay, we're seasoned optimizers. You all do supply chain optimization or scheduling of patients in hospitals, or scheduling of renewable energy. So you know all these questions. So, but just to sort of go from the start, optimization is really the art of finding the best solution from a collection of alternatives. And when we solve an optimization problem, a lot of times it's very hard to actually ensure that you have the best solution. So that's actually a very, very strong statement, and Pietro will later tell you why this is very hard often. If you see somebody who's really tall, you might be tempted to say, wow, you're the tallest person on the planet. But to make that statement, you have to know every other person on the planet. So that's a strong statement. And assuming there's no Guinness Book of Records. Optimization happens in all areas. And one of the exciting parts of working at a government lab is that I see scientists from many disciplines working in optimization. I'll show you one in a moment, design of experiments. So we have physical experiments that we're conducting. They're often expensive, like you're drilling holes in the Arctic to get ice cores and extract information about the sea ice, for example, or Antarctica, about the ice shelves. And that's very important to predict how these ice shelves are going to behave for the next 50 or 100 years. That's a very challenging problem. Many of you probably know about power grid control and design. So how do you design an efficient power grid? How do you control this power grid? How do you make sure the lights stay on? That's non-trivial. And in fact, someone once described the US power grid, which is probably much, much smaller than the Indian power grid, as the most complex machine ever built. Really complex problem. Finance, there are many applications. In medicine, the dose design for radiation therapy, for example, So you have a human body, and somewhere in the body there's a tumor. And so you want to zap it with X-rays or radiation. And the more you zap the tumor, the better, because the tumor dies. So that's great. At the same time, next to the tumor, there's often other things like eyes and noses and organs that are very important to the person. So you don't want to zap those because you're going to kill the patient. So that's a very interesting optimization problem where you're balancing actually two different objectives. Kill the tumor, but let the patient live. And I don't know, you can probably decide which one is more important. Economics, so we have somebody here with an economics background. There's an interesting problem in the optimal transition to clean energies. You can formulate this problem and design policies on how you encourage consumers, for example, to adopt electric cars or alternative energies. And so this optimal transition is something that happens a bit like a logarithmic log transform over time. And if you have an objective of doing this as quick as possible, then you can think about what incentives you provide, tax incentives, reduced, or money that you give to the people. And then lastly, big data, machine learning, the training of neural networks, that's a sort of emerging area. And there's a lot of optimization in it in terms of training these networks, reducing the loss function. There's some integer optimization that one could apply there that has been applied, where you're selecting the depth of your network and the breadth of your network. Those are integer variables. Or you can optimize the individual activation function inside your networks. And we'll try to give some detailed examples throughout the course. So there's lots of optimization. And if you want to know more, I know a lot of optimization problems. I'm not going to be able to tell you about all of these. But here's one problem that I'm working on right now at Argonne, and that's the optimal placement of environmental sensors. So on this slide, you see two problems, actually. On the left-hand side is these first two pictures are a very simple toy problem, toy example. The right-hand one, does anybody know what's depicted there, what is shown? Does anybody recognize this country or island? Greenland, brilliant, okay. What we have in these examples is we have a model of the physical world. So in this first example here, this is maybe a very simple urban area. There's two houses here. It's a two-dimensional urban area, so it's very simple. But we can do this in 3D as well. And somewhere in this urban area, there's some contaminant that is released. And then this contaminant passes through this area following an advection diffusion equation. That's a partial differential equation that tells you how this is an initial condition, will be distributed over time. What we're interested in is we don't really know, typically we don't know where this initial contaminant is, and so we're interested in finding out where a contamination happened so that we can send a team there to remediate it somehow, shut it down in some way. And so typically what we do is we have locations. These yellow dots are sensor locations. So you could imagine having sensors on your houses that measure the air quality, for example. And what you want to do is you want to place these sensors at locations. So here I have 16 potential locations, but you can imagine having many, many more locations. And the goal of a design of experiment problems is to tell me where do I place these sensors so that no matter where the initial release happened, I detect it as quickly as possible. So I want to be able to, from the measurements, I only make measurements at discrete locations. I can't make measurements everywhere. From these measurements, I want to be able to invert for the initial location. But now I want to have an arbitrary initial location. So no matter where the initial location is, I want to find out as quickly as possible where this was. And so the placement of the sensors, those are binary decision variables. You either place a sensor or not. The sensors are expensive, so you probably have an upper bound on how many you can afford. And there's a nonlinear process that goes then from the measurements that you make of the sensors back to the initial condition. And typically we maximize some kind of information gain or minimize the variance so that we get as accurate a picture as possible. So we're looking at this at the moment, but really what we want to understand is the uncertainty of the sea ice in Greenland. And so what you see on the right here is the uncertainty in the magnitude, in the depth of the sea ice. So does anybody know how deep the sea ice is in Greenland? How many meters? Or guess? Kilometer? A kilometer? Anybody has more than 1 kilometer? 3 kilometers. That's the thickness of this ice. If that all melts, there's just a chain of islands left around Greenland. The uncertainty is about 600 meters. And so knowing this uncertainty, and reducing this uncertainty is important for us to understand how quickly the sea ice moves off Greenland, because the thickness allows us to understand what's actually underneath the sea ice, which is the friction, the basal friction. And we want to understand these basal friction parameters to predict when the sea ice is going to move off. Now, I don't know if you can see it, but what they do typically is they fly aircraft in straight lines across Greenland to measure the thickness with ground penetrating radar. What we want to do is basically have curvy flights that reduce the uncertainty in a better way. And so designing a trajectory is a really hard problem. And this is a very challenging problem. So this is to model the sea ice here, you can no longer use an advection diffusion equation. You have a Stokes flow. Those are very complicated, complex codes with complex discretizations. Okay, so that's sort of the motivation, and I'm going way too slow. So ingredients of an optimization problem. So here's a way of writing down an optimization problem. We'll use this notation throughout the course, or a similar notation. We have an objective function, and there's a spelling mistake there. There should be an I there, so I need to correct that. That basically tells us how well we're doing. So minimize the cost of placing the sensors, for example. Our decision variables are X and Y, and we typically use X for continuous and Y for discrete decisions or integers. And then we have what I wrote down as 3 classes of constraints, and there's actually more classes, more distinctions within these classes. So the simplest ones are these simple bounds that just say your X has to lie between some lower bound and some upper bound, for example, and the lower or the upper bound could be infinite. So in some cases, those could be 0 lower bounds. So the pressure, for example, if you look at Stokes flow, the pressure is non-negative. Y, and you have bounds on Y. And then there are some affine or linear constraints. And again, we can write them either with lower or upper bounds. If the lower bound is the same as the upper bound, then those are equations or equality constraints. And the most general constraints are these nonlinear constraints here, where we have a nonlinear function g of x and y that is between these 2 bounds. And again, if the bounds are equal, we have an equation, and then any of the bounds can be either minus infinity or infinity. If they're both minus infinity and infinity, then there's nothing, no constraint. Okay, that's okay, I hope. You've seen optimization problems before. I'm going to write this more compactly in many of the cases because there's just so much room on only so much room on the slides. So I'm just going to write f of x and y. That's the same objective, but now I just assume I have these nonlinear constraints and some integrality condition on my integers y. But I can take any other problem that I have and put it into this form. And you probably have seen slack variables or surplus variables that you add to your problem to make it look like this problem. And of course, any linear function can be expressed as a nonlinear function. That's just a linear function, it's just a special case of a nonlinear function. So there's no loss of generality here, but it will make it easier for us to explain the algorithms. And so just for some terminology, these constraints, there's m of these constraints, and so each of these individual functions then maps Rn and z to the p, so those are our integers, into R. So our constraints are real, our objective function is real. You can have complex constraints, by the way, and complex variables, but then you need to split them up into real and imaginary part. And that will happen when we look at the power grid. So we're going to make some basic blanket assumptions, and we'll violate them towards the end. So the first is that our problems are finite dimensional. So our variables live in a vector space Rn cross z to the p, and n and p are finite. So we're not looking at Hilbert spaces, function spaces yet. We'll do that later. But then we'll always discretize. And the problems I showed you at the very start with the advection diffusion equation, those are not finite dimensional. Those are infinite dimensional function spaces. And we're also going to assume that the functions that we have, and there's a typo here, this should be a g, they are smooth, or at least twice continuously differentiable. So I can differentiate those functions. I can use traditional first order conditions, for example, for optimization, and I'm allowed to do that. We can relax some of those conditions, but it makes the a lot easier. And then whenever I have a more general form of problem, then I can get back to this. I can rewrite it in this problem, either by pretending that my linear function is really, one of my nonlinear functions is a special case of a linear function, or the other way around. But solvers, the solvers that we'll introduce and talk about, they will in general exploit additional structure. So the additional structure, if it's there, we want to expose it to the solver, and they exploit things like linearity, for example. Okay, so one of the things we do here is optimizers seem to always minimize. And you can say, what about if I don't want to minimize my profit, I want to maximize my profit. The good news is you can just turn this function, your objective function, upside down. So if you want to maximize a function f of x, that's this blue function here, you want to find a maximum point, this point here, then what you do is you just invert the sign of f of x, you just flip it around the 0 axis here, and now you have a function that looks like this, and it turns out that if you find the minimum of this function, then that corresponds to the maximum of the other function, and you just have to remember that there's now a minus sign that goes with the objective value that you need to carry out. So we will only consider minimization. Does everybody know what W log is? It's a weird logarithm, or without loss of generality. Okay, good. Excellent. I have all these abbreviations in there, and please ask. Some of them are from my time when I did my PhD. So we've already talked a little bit about notation. If I have a vector in Rn, an n-dimensional vector, then I just call the components A1 through An. And for two vectors, inequality means that it's taken component-wise, the inequality over each of the components. I'm not going to stick to this. In fact, on the next lecture, I will use uppercase letters to denote individual variables, but most of the time I try to stick to a notation where I use matrices are capitalized. And we try to use calligraphic type to indicate sets. That could be finite or infinite. So for example, they could be index sets. A could indicate which activities are happening, or they could be subsets of Rn, like a box with lower and upper bounds. And then you've heard this probably, and this will happen throughout the course. We're trying to use optimization to denote optimization problems. A few years ago, there was a big debate about whether we should move there, and some people still prefer programming. And so sometimes optimization problems are also called programs. And that goes back to some of the work that George Danzig, who was one of the pioneers, the grandfathers of optimization, was doing in World War II, when he was solving linear programs which were basically scheduling problems to get supplies out to the Pacific for the American forces fighting there. So that was a program that was done then. But since then, if you think of a program, you think of something like Python, C++, maybe Fortran. So we prefer to use optimization here. And I will no doubt use programs somewhere in my lecture. So you can just correct me at that point, please. Okay. So one of the things that we'll try to emphasize here a little bit is modeling. And I know you have done a lot of modeling because you've done supply chain modeling and other modeling. You do crew scheduling. But there's some aspects that in mixed integer nonlinear optimization that are sort of more flexible, give us more opportunity for doing cool stuff, but also for making mistakes. And so we place some emphasis on the modeling. And there's a very nice book by somebody called Williams, who was at the University of Southampton, on mixed integer linear programming, or MINLO modeling. And so we'll look at some of the aspects in nonlinear optimization here that are important. We often like to reformulate nonlinear relationships so that they're convex or maybe even linear, because then it's easier. So the best way to solve a mixed integer nonlinear optimization problem, does anybody know what the best way to solve a mixed integer nonlinear optimization problem is? What?
Solve a linear program.
Yes, you solve a linear program. If you can reformulate it as a linear program, if you don't have nonlinear, you're done, you're golden. So if you can do that, that's always good. That doesn't always happen. And so we like linear, which is easier than convex, which is easier than non-convex. And we'll keep talking about this throughout the course. So here's a little example that comes from Chris Fluders' book on mixed integer nonlinear programming. It's a chemical engineering process synthesis problem. There is a chemical engineer here. Who's the chemical engineer? Yes. Synthesis means design, right? So it's just another word for design. And the goal here is you have some output, C, you have some raw materials, A and B1, and you want, or A and B, and you want to create, there's another typo there, this is terrible. You want to create C from these two raw materials. And in doing that, you have the option of splitting this A material. You can either process it in this process 3, which gives an intermediate B3, or you can process it in process 2, which gives an intermediate product B2. And so the question is, which one of those two should you choose to maximize your profit in the end? So we can model this. We introduce some process choices, binary variables y1, 2, and 3, that basically tell me, is this process present or not? Do I want this process or not? And then with these binary variables also come some bounds that tell us the flow that goes out. So if I don't choose to do y1, if I don't choose to have this process, then there's no C that's being produced. All these variables are non-negative. Similarly for B2, if I don't do process 2, then there's no B2 produced. And the objective is basically cost minus revenue. So you want to maximize revenue, which is why we negate it here, and minimize the cost. And then the objective is put together out of two parts. There's an investment cost and some revenue. So if you build these processes, there's a certain investment cost. Those are just numbers. And there's some cost involved in that. And then the revenue is however much you produce of the C minus some cost of the raw materials that are either the A's or the B1s. And then you can set it all together for a final objective function value. There's some nonlinear constraints here that have to do with mass balances in the network. There's a mass balance here which involves B2, B3, and C. So whatever comes out of this process is a combination of B3, B2, and B1. So there's some loss obviously there. So that tells you how much of C2 you're producing given the inputs B1, B2, and B3. And then the other two processes have some nonlinear relationship that produce B3 and B2 out of A3 and A2. And those are just logarithms, for example. And then there's a constraint that says you can have at most one of these two processes equal to 1. So this constraint, together with the fact that these variables are binary, implies that you can have y1, y2 equals to 1, y3 equals to 1, but not both. But you can also set them both to 0, right? 1 plus 1 is 2. That's too big. Yeah, sorry. Yeah.
I just want to know that what is the upper bound for C? Is it like go up to 1?
Yeah, that's just in this case, the upper bound for C is just 1. It's but we could have had another upper bound. So it could have been whatever material, how big this would be a reactor, typically in chemical engineering, and so the capacity of the reactor.
It could be a bigger.
Yeah, absolutely. This is just for simplicity, I think, that Chris used this. Good question. Okay, so the final model, there's sort of this mix of some nonlinearities, some binary choices, and they're all coming together in one optimization problem. So that was sort of the first simple example. And our chemical engineering expert can give you much more complicated examples. You can design distillation columns, for example, where you have a product flow coming in, and then you have trays, and you can optimize the number of trays, for example, in the distillation column to make sure that the product that comes out of the top has a certain purity. That's a very nice problem. Okay, so we showed you an optimization problem. It's ingredients, so there's an objective, there are variables, there's constraints. So that's fairly standard. That's the same that you have in all your optimization problems. And I sort of briefly introduced this very first problem, but please do what your friend did at the back and ask questions. That's really great. And with that, we're finishing 2 minutes early. So that means you have 2 minutes to ask more questions.
Sir,
Yeah.
the mass balance, you have a mass balance constraint here. That is C minus something 0.9. In the next
Yeah.
slide.
Oh, the next.
Yes, process 1.
Mm-hmm.
It is C minus 0.9. So, can you explain the first process 1? It will go up to 1 or 0.9. How it will proceed, like C minus 0.9, B1, B2, B3. So C will take up to maximum value of 1.
Yeah.
And then the other part 0.9, B1, B2, B3. So it will take the maximum value of 0.9 and something how it will work. So what will be the value of B1, B2, B3? Just I'm asking like how the equation will satisfy.
Oh, okay. So I have an upper bound on C, which is 1. Now, let's assume that I do B1 plus B2. And so B2 had an upper bound of 0.9. So now 0.9 times 0.9, you need to help me out. That's 0.81. But that means the most I can put in terms of B1 is sort of 0.19.
Okay.
But I can also have less of a product or less of B2. If I want to make less of B2, then I would put in less of A1. So I have this balancing that I can do. I can choose how much I put in to this product stream here versus the product stream at the top. And somehow they're both combined to make this product. This is a very, very simple example, I think. I don't think this is a realistic one. But I can mix, or I can generate C2. There's some loss that happens inside this process, which means not everything that goes in comes out. There's this factor of 0.9. And I can now choose how I balance these things.
Yeah.
Cool. Yeah. Oh, gosh. Yeah.
What does one flow means? I mean, there is no unit of measurement.
No, there's no unit of measurement here. So I'm not doing. This is not a realistic example. So it's just an arbitrary. One is an arbitrary number here, but we could have had different ones. We could have had units of flow, and then it could be kilograms per hour or something, and then that would be a different unit. That would depend on the size of these reactors, for example, that are happening there. So the one is not a good constant, one, because it's too generic. But that's the simplest example that I could find, so I apologize for that. Yes?
But I think any process can just realize between 0 and 1. So we know the capacity we divide and we convert to 1. So I think it could be actual examples.
It could be, yeah. But it's a little bit cooked up because the other numbers are 0.9, I think. So those two are 0.9. So I don't know how realistic this is.
Actually, if we divide everything by C,
yeah,
any number, we can convert this to 0.
We could, yeah. So it's a unitless problem. It's not. Don't take too much stock of this problem. It's not a good example, maybe. The main thing was the functional forms. You have linearities, inequalities, nonlinear expressions, an objective, and constraints. And a picture that tells you something is happening there and you want to optimize this. Cool. Yes?
So this is a question about history. So in integer programming, the early examples tend to be about traveling salesmen from 1960s or around that time. So do you remember, what were the early examples of MINLPs, or are chemical engineers the first ones to start thinking about them?
Yeah, so the chemical engineers were sort of the first group of people who thought about mixed integer nonlinear optimization. Mainly, I think, driven by applications like distillation column design. And there was a group at Carnegie Mellon University with Art Westerberg, Larry Biegler, and Ignacio Grossman, who were early pioneers in mixed integer nonlinear optimization. And so that was sort of in the, I wasn't around then, but I think it was in the 80s or so that they started it off. And then Chris Fluders is a student of Ignacio's, I think. And so they were all, there's a group of chemical engineers that have worked on this for a long time.